Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, Assalamu alaikum. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Today, the topic of our presentation is instrumentation and some spectral interpretation. The course code is CHEM451 and today is the 25th lecture of molecular spectroscopy. As you know that we have discussed some of the aspect of instrumentation of IR spectroscopy. So as I told you that the main difference between UV visible spectroscopy and IR spectrophotometer is the light source, that in this case the light source used in IR spectroscopy produce IR radiation, while in UV visible spectroscopy the light source used produce UV visible spectroscopy. So the basic requirement for the light source in IR radiation is that it must produce IR radiation. And the other thing is, one of the basic thing that we can't do in IR spectroscopy, that can't use glass, because the glass itself, made of silicates, itself absorb IR radiation. So we can't use glass in IR spectroscopy. And several possible types of light sources are used in IR spectroscopy. For example, the first one is Nernst-Glauer. What is Nernst-Glauer? So this rare earth metal oxides like zirconium, cerium, thorium, these elements are heated electrically. So, and then apply current to the cylinder. This has resistance to current flow. So this generate heats of a 1200 to 2200 degrees centigrade. So causes light production. This is quite similar to the black body radiation, as you know from your interclass physics that what is black body radiations. So this light source produce light which is quite similar to the black body radiation. The range of use of this IR source, light source, is from 600 to 10,000 wave number, centimeter inverse. So this need a good current control or overheats, because it can be damaged if you don't have a current control and heat control over it. So as I told you that in several types, the second type of light source in IR spectroscopy is Glober. This Glober is quite similar to the Nernst-Glauer. What we do in a Nernst-Glauer, the rare earth metal oxides like zirconium, we heat it electrically, and then then current flow, and then heat is generated and light is basically emitted. But this one, this Glober, used silicon carbide rod instead of zirconium cerium or thorium of rare earth metal oxides. So the range of use of this global light source in IR spectroscopy is quite similar to that of Nernst glove. The next one, the third one is incandescent wire source. This is tightly wound nichrome or rhodium wire instead of that rare earth metal oxides, metals or silicon carbide that is electrically heated. Same principle is Nernst Glauber is used, but the difference is that here the tightly wound nichrome or rhodium wire is used. This lower intensity than Nernst Glauber or Glauber, but longer lifetime in comparison to the first two light sources used in IR spectrophotometer. The next one is carbon dioxide laser. Carbon dioxide laser gives mixture of 70% helium, 15% carbon dioxide, and 15% nitrogen. So a voltage is placed across the gas, exciting nitrogen to lowest vibrational level. The excited nitrogen populate the asymmetric vibrational state in carbon dioxide through collision. Infrared output of the laser is the result of transition between rotational states of carbon dioxide molecule of the first asymmetric vibrational mode to rotational states of both the first symmetric stretch mode and the second bending mode. Gives off band of 100 centimeter inverse in the range of 900 to 1100 centimeter inverse. This light source is having a small range but can choose which band should be used. And the good thing about this light source is that many compounds have IR absorption in this region. This light source is a much more intense than black body sources. The other light sources are mercury arc, which is having this used in the far IR region, and the tungsten lamp range is from 4,000 to 12,800 centimeter inwards and used in the near IR region. So, coming to the detector used in the IR spectroscopy, two main types are in common instrument. One is thermal detector, and in the thermal detector, two pieces of dissimilar metals fuse together at the ends. When heated, metals heat at two different metal heats at different rates. So potential difference is created between the two different metals that varies with the difference in temperature, usually made with a blackened surface to improve heat absorption, to improve the absorption of all the heat, I mean black black surface. So this is then placed in evacuated tube with the window transparent to IR, not glass or quartz. So IR hits and heat one of the two wires. This can use several thermocouples to increase the sensitivity of these metals. So again, coming to the principle of this thermocouple detector, in this thermocouple detector, basically two metal plates of a different metals are used, and these two plates are placed in a vacuum tube with this window which is transparent to IR radiation. This is at least not made of a glass or quartz, because glass or quartz absorb this IR radiation. Then these two metal plates are basically connected to the fused together at the end. When these are connected to the potential, and potential difference is created between two metals with varies the difference in temperature. Usually this is made of a blackened surface to improve heat absorption. So when this IR radiation heats one of the two wires like this one, so can use several thermocouple to increase their sensitivity. So the second one is bolometer. This is a strip of the second type of this thermocouple detector is this strip of metals, platinum and nickel. These platinum and nickels are semiconductor that has a large change in resistance to current with a temperature. So as light absorbed by a blackened surface, resistance increases and current decreases. This is a very sensitive type of detector. The next one is photoconducting detectors. Thin film of semiconductor, lead sulfide for example, on a non-conducting glass surface. This is a non-conductive glass surface, and this is a thin film of semiconductor like lead sulfide, and this is sealed in a vacuum. So when sealed in a vacuum, absorption of light by this semiconductor, this thin film of semiconductor, from non-conducting to conducting state. This is going from non-conductive to conducting state. So decrease in resistance usually increase the current. The range is from this to this at a room temperature. So this is the photoconducting detector. The next one is pyroelectric detector. So in a pyroelectric detector, usually ceramic or lithium tantalate materials get polarized, separation of positive and negative charges in presence of electric field. So this is a temperature dependent polarization. Basically this measure the degree of polarization related to a temperature of a crystals. This is giving a very fast response. Usually this is quite good for FTIR. So the other components are sample cell, where usually you place the sample cell. This must be made of IR transparent material. For example, KBr pellets or sodium chloride pellet. So what does it do? Because when you place your sample inside that sample cell, it must be IR transparent, because if your material is absorbing IR radiation, it is giving you interferences, which is not giving you an accurate result. So all the light should reach to the sample without interference of the material which is made of the sample cell, which is made of either sodium chloride or KBr pellets. The other component is monochromator. So usually reflective grating is common. Can't use glass prism, sense, absorb IR radiation. The principle of the monochromator, as we discuss it in UV visible spectroscopy, is similar. That it absorb other radiations and only allow the radiation of that wavelength, which is quite near to the wavelength absorption maxima of your analyte, your sample. So we are not going into the detail of a monochromator because we have discussed that in UV visible spectroscopy. So this is how the overall instrument look like. That it in this like this is a chopper. It needs chopper to discriminate a source light from a background IR radiation. So after the chopper, monochromator after the sample cell is used. So when we place the sample in a sample cell, after that this is monochromator is. So not done in UV visible, since letting in all to sample may cause photo degradation, too much energy. So as IR is a lower energy radiation. Advantage that allows monochromator to be used, screen out more background IR lights. Source problems are that source weak, need long scan, detect response slow, rounded peak usually in IR spectroscopy. So the other type of IR spectroscopy is, we are just touching it, Fourier transfer IR spectroscopy, which is shortly called FTIR. This is alternative to normal IR spectroscopy, based on Michelson interferometers. So the principle is that light from source is split by central mirror, uh, this central mirror, into two beams of equal intensity. So beams go to the other mirror, reflected by central mirror, recombines and pass through the sample to detect two sides of mirror, one fixed and other is movable. So move second mirror, light in two path, travel different distance before. So this is constructive and destructive interference. As mirror is moved, get change in signal. So we are not going into the detail of FTIR because FTIR is not the part of this course. So the advantages of FTIR compared to normal IR spectroscopy, that it is much faster, because these one needs seconds in comparison to normal IR spectroscopy, which needs and needs minutes. So use signal averaging to increase signal to noise ratio. Signal to noise ratio is a very important, because if your noise is more and your signal is low, you can't see anything in your spectra. So what does it do? Basically, you are going to the signal to noise ratio. You are making this noise low as possible. You are making this signal high as possible. Then the ratio is, means if your signal is high, it is divided by a very small noise if it is small. But even if your signal is high, but it is divided into a very high noise, still it is not giving you a good C of your spectra, your analyte, your analysis. So this is high inherent signal to no slit, less optical equipment in FTIR spectroscopy. High resolution is also one of the important key parameter of FTIR spectroscopy. Yes, of course. FTIR have some disadvantages associated to it. Like it is a single beam, it require collecting blink, can't use thermal detector, that is too slow for FTIR. So in normal IR, scan through a frequency range, and FTIR collect all the frequencies at once. So this was the small comparison of FTIR spectroscopy compared to normal IR spectroscopy. So coming to the application of IR spectroscopy, IR spectroscopy is generally a qualitative technique. How? Because I told you that IR spectroscopy, you are using it mainly for the identification of different functional groups. So it is used in combination with other technique like NMR and MS spectroscopy. As I told you that all these combination technique, all these analytical technique like MS spectroscopy, MS spectrometry, UV visible spectroscopy, although UV visible people are using it very less nowadays in modern world, or in this specifically this identification work and even to the quantification work, these are very sophisticated technique like HPLC, hyphenated technique, HPLC connected to mass spectrometer, HPLC connected, electrophoresis connected to other techniques. So these are used. But this IR in combination with NMR and MS, basically in late 1950, revolutionized the organic chemistry, the identification chemistry. This decreased the time to confirm the compound identification 10 to 1,000 fold, at least I would say. This IR technique usually gives you a general scheme that what functional group are present by looking at group frequency region from 3600 to 1200 centimeter inverse, because this is usually a fingerprint region. This is the area in a spectroscopy which we are used for the identification. So as I told you that in a modern world, this after the 1950s, the combination of these two techniques, because once you confirm the functional group that this functional group is present, either for example this carboxylic acid is present or alcohol is present, and then you are going to the other technique NMR, and then to MS some fragmentation pattern, some structure information with NMR, identification of hydrogens, identification of different carbon, and then the environment of the carbon, and then by the application of all these, you are using this IR in combination with this with other spectroscopy technique. So here is the like in a previous slide, as I told you that this is example of a spectrum. And this is the wave number from usually from 1200 3700, as I told you, from 500 till 1200 or 1500. This is a fingerprint region, a skeletal vibration. So this is a spectra. So different groups like functional groups shows absorption or means transmission in a different region. Some in 3000 wave number, some 2000, some 3500, which is typical for any specific group of compound. Here is the list of all those compounds. Which is showing absorption in the IR spectrophotometer. Carbon and hydrogen, the bond of carbon and hydrogen of alkane, this typically show absorption in the range of 2550 to 2970. So this is intensity is quite strong. So whenever you have a spectra and absorption is in the range of 2550 to 2970, so you must say this is due to the carbon hydrogen, means alkane. So if there is any double bond, if the vibration of this carbon and hydrogen, so this is because this is different than alkane, because here double bond is attached. So the range, the absorption range of alkene is from 3010 to 3095. So it means that this is a medium and also a strong. And the absorption range for the triple bond alkyne is, for this hydrogen, is 3300, so which is quite strong. And absorption range for carbon hydrogen bond aromatic rings, so usually this is 3000 to 3100, which is medium. And for alcohol range is here, and monomeric alcohol, and then for phenol, hydrogen bonded alcohol, phenols, monomeric carboxylic acid, hydrogen bonded carboxylic acid. The range is this one, and intensity is variable, sometimes broads, medium, broad. And for nitrogen and hydrogen, like amine or amides, the range is this one, and it is medium. Uh, so you can't confuse it with alkyne, because alkyne is 3300 as well. This is 33, but this is alkyne is strong, and this one is medium. Then you immediately recognize it, that basically this absorption is due to the amines or amides. And then this was carbon and hydrogen alkane vibration. But if it is carbon carbon vibration alkenes, the range is automatically dropped to 1610 to 1680, and the intensity is variable. Similarly, aromatic ring, carbon carbon double bond, which is conjugation, so it is different than alkene, because alkene is this one is 675, and the absorption for carbon hydrogen is this one, but for double bond this like this one. But this alkene, this aromatic ring conjugation, so 1500 to 1600, this is different than this alkene, because conjugation is involved in aromatic ring in comparison to the normal alkene. And alkyne, so this absorption is 2100 to 2260, and also the intensity is variable. So for nitriles, intensity is strong. Alcohol, ether, carboxylic acid, also the intensity is strong. Aldehyde and ketone intensity is strong, and the range is given here. So this is a very important table. You should remember this table, because whenever you are interpreting the spectra, so immediately your mind go to that place, that okay, this functional group is basically present in the spectra. So this is the example of IR spectrum of alkane. Alkane have no functional group. Their IR spectrum displays only carbon-carbon and carbon-hydrogen bond vibrations. So of these, most useful are the carbon-hydrogen bands, which appears around 3000 centimeter inverse. So this is the spectra for alkanes. So since most of the organic molecule have such a bond, so most organic molecule will display those bands in their spectrum. So first of all, whenever you are looking these around 3000, automatically your mind goes to carbon hydrogen stretch, which is in the 3000 stretch, and carbon hydrogen stretch is around this one. So this is around 1400, means 1500. So this is carbon hydrogen carbon. So one is carbon carbon, other one is carbon hydrogen. So this is IR spectrum of alkane. This is example of N-hexane. So the spectra of N-hexane is given. The source is I have taken it from LG Organic Chemistry 5th edition, Pearson Education 2003. Weird Organic Chemistry 5th edition. So this is the IR spectrum of alkene. Beside the presence of carbon-hydrogen bond, Alkene also shows sharp medium bonds corresponding to carbon double bond stretching vibration about 1600 to 1700, while some alkene might also show a band for carbon hydrogen band stretch appearing around 3000 is shown below. However, this band could be obscured by the broader band appearing around 3000. This is quite broad. So hopefully you understand this, and inshallah next we will discuss the more detail the interpretation of spectra.